Chemistry is absolutely all around us, in every single thing you see and touch. Think about the air you breathe this very moment. That's a mix of gases, and their interactions are pure chemistry. Consider the food you eat for energy, the water you drink to stay hydrated. It's all governed by chemical principles. Chemistry is the science of stuff, what it's made of, how it behaves, and how it changes from one form to another. Isn't that pretty cool? Understanding chemistry fundamentally helps us understand the intricate workings of the world. From the tiniest invisible particles to the vast distant stars, chemistry plays a crucial role. It's not just confined to sterile laboratories. It's happening in your kitchen as you cook, in your garden as plants grow, and even inside your own body as you live and breathe. Now, if you're an aspiring medical professional, a dedicated NEET aspirant, chemistry is incredibly important, a real cornerstone of your studies. It forms a significant portion of the NEET examination, and for good reason. A strong understanding of chemistry directly helps you comprehend complex biological processes, like how different medicines interact with our bodies or the biochemical pathways that keep us alive. Think about it. The process of digestion is essentially a series of complex chemical reactions, breaking down food. Respiration, the way we get energy from oxygen, that is more chemistry in action. So, building a solid grasp of chemistry basics is your golden ticket to acing the NEET, and more importantly, becoming a knowledgeable and effective doctor or healthcare professional. It's a truly foundational science you cannot afford to overlook. This comprehensive guide is specifically designed to help you, the ambitious NEET student, master those essential basics. We're going to take some concepts that might seem tricky or intimidating at first and break them down into simple, easily digestible, bite-sized pieces of information. We'll make extensive use of pictures, diagrams, and relatable examples to make the learning process not only effective but also fun and engaging, ensuring the knowledge sticks. Think of this guide as your friendly, approachable chemistry companion, always ready to explain things clearly. Together we'll explore the fundamental building blocks of everything in the universe and delve into how these tiny components interact with each other. There's absolutely no need to be scared of complex formulas or daunting equations. We'll tackle them systematically, one step at a time, building your confidence along the way. So, get ready to put on your metaphorical science goggles and prepare for an exciting journey. We're about to dive headfirst into the amazing, often surprising world of chemistry. We will carefully examine what matter truly is, explore how it can transform from one state to another, and uncover the fundamental rules that govern these fascinating changes. By the time you reach the end of this guide, you'll see that chemistry isn't just another subject to be memorized. It's a powerful way of thinking, a lens through which you can understand the universe in incredible detail. And for your NEET aspirations, it's an indispensable key to unlocking your future success. Let's get started on this scientific adventure together. Consider this your launchpad into the molecular world. First things first, let's tackle a big question with a surprisingly simple answer. What exactly is matter? Matter, in its most basic definition, is anything that has mass and takes up space, which we call volume. Just look around you right now. Your sturdy desk, the informative book you might be holding, even the invisible air you're breathing in and out. It's all matter. Indeed, you yourself are made of matter. If you can theoretically weigh an object and it demonstrably occupies some amount of three-dimensional volume, then congratulations, you've successfully identified matter. It truly is the fundamental physical stuff that constitutes the entire universe, from the smallest speck of dust to the largest galaxy. Everything tangible is matter, folks. Matter possesses characteristics that we call properties. These properties are like its unique identifiers, helping us distinguish one type of matter from another. We can describe matter using its physical properties, such as its color, odor, melting point, boiling point, or density. You can observe these physical properties without changing the fundamental chemical identity of the substance itself. Think about a piece of ice. It's a solid. It feels cold to the touch, and it's often transparent. Those are all distinct physical properties. Then we have chemical properties, which describe how a substance can transform into a completely new substance through a chemical reaction. For instance, the tendency of iron to rust when exposed to air and moisture is a classic example of a chemical property, showing its reactivity. Imagine you have a tall glass of refreshing water. That water is undeniably matter. It clearly has mass. You can feel its weight if you lift the glass. And it definitely takes up space within the confines of the glass. You can see it, you can feel its coolness, and you can even measure its volume. Now let's consider the air filling the room around you. You can't always see it directly, unless it's smoggy or dusty, but it's most certainly there, pressing against you from all directions. Air fills the entire room, and it also has mass, even though it's very light compared to solids or liquids. Scientists have developed clever methods like using sensitive balances to precisely measure the mass of air, proving its material nature beyond any doubt. It all comes down to careful observation and precise measurement, the hallmarks of good science. Understanding the concept of matter is absolutely fundamental to the study of chemistry. It serves as the essential starting point for everything else we're going to learn and explore in this fascinating scientific discipline. We really need to know what we're working with, what this stuff is, before we can begin to comprehend how it reacts with other substances or how it undergoes various physical and chemical changes. So always keep this crucial definition in mind. Mass and volume are the two key identifiers of matter. It's the stuff that makes up everything you can imagine, from a tiny, almost insignificant grain of sand on a vast beach to a colossal, awe-inspiring planet orbiting a distant star in our solar system. Keep that definition handy in your mental toolkit because it's a big one. Matter, as we've established, isn't just one uniform thing. It comes in different forms, or what scientists call states. The three most common states of matter that you encounter in your everyday life are solid, liquid, and gas. A perfect and simple example to illustrate this is water, our good old friend H2O. Water can exist as ice, which is its solid state, hard and crystalline, as liquid water, the familiar liquid state, flowing and taking shapes, or as steam, its gaseous state, invisible and expansive. It's incredibly important to remember that it's the exact same chemical substance, H2O, in all three states, but it behaves very, very differently in each one. This difference in behavior is primarily because the tiny particles, molecules in the case of water, within the matter, are arranged and move in distinct ways depending on the state and the energy they possess. It's all about particle power and their kinetic energy. In a solid, the constituent particles, atoms, ions, or molecules are packed very tightly together, often in a regular, repeating geometric pattern called a crystal lattice. They vibrate energetically in their fixed positions, but generally don't move around freely from one place to another, much like people in assigned seats at a theatre. This rigid arrangement is precisely why solids have a definite, unchanging shape and a definite fixed volume. Think of a sturdy brick, a shiny diamond, or a metal spoon. It stays brick-shaped, diamond-shaped, or spoon-shaped no matter where you put it. In liquids, the particles are still quite close together, maintaining contact, but they are not held in fixed positions and can slide past one another, allowing the liquid to flow and adapt. Consequently, liquids have a definite volume, but take on the shape of whatever container they are poured into. Pour water from a tall, thin bottle into a wide, shallow glass. Its shape changes dramatically, but the amount, volume, of water remains exactly the same. Now let's consider gases. In a gas, the particles are much, much farther apart from each other compared to solids or liquids. And they move around randomly at very high speeds, constantly colliding with each other and with the walls of their container like tiny, energetic billiard balls. Because of this freedom of movement and large intermolecular spacing, gases have no definite shape and no definite volume. A gas will always expand to fill the entire volume of any container it's placed in, regardless of the container's size or shape. Think about the enticing smell of freshly baked popcorn cooking in the kitchen, or the fragrance of a flower. Those aromatic particles are actually gases, rapidly spreading by diffusion throughout the entire room. The particles are zipping around in a chaotic dance, bouncing off everything in their path. It's a veritable particle party, and they're full of motion. One of the most fascinating aspects of matter is its ability to change from one state to another, a process called phase transition. This transformation process is scientifically termed the interconversion of states. For instance, applying heat energy to a solid can cause it to melt and turn into a liquid. This is called melting or fusion. Further heating a liquid can cause it to boil and transform into a gas. This is called boiling or vaporization. Evaporation is a similar surface phenomenon. Conversely, removing heat energy by cooling a gas sufficiently can cause it to condense and turn back into a liquid, condensation, like dew on grass. And cooling a liquid further can cause it to freeze and become a solid, freezing or solidification. These changes are all physical changes because the chemical identity of the substance doesn't change, only its physical form. Water is still H2O, whether it's ice, liquid water or steam. Its molecules remain intact. We've established what matter is and its different states, but it's important to realize that not all matter is created equal in terms of its composition. We can broadly classify matter into two main categories to better understand its makeup: pure substances and mixtures. This classification system is incredibly useful as it helps us organize our understanding of the vast array of materials found in the universe. A pure substance is defined as a sample of matter that has a fixed, definite chemical composition and a distinct set of characteristic properties like a specific melting point or density. Crucially, a pure substance cannot be separated into simpler substances by ordinary physical means like filtering, sifting or decanting. Think of pure gold, Au, which is made of only gold atoms, or pure distilled water, H2O, made only of H2O molecules. They are uniform throughout and possess consistent properties. Pure substances themselves can be further divided into two more specific categories: elements and compounds. Elements represent the simplest form of a pure substance. They are the fundamental chemical building blocks of all matter. They cannot be broken down into any simpler substances by any chemical means. You can't get simpler than an element through chemical reactions. Examples you're likely familiar with include vital oxygen, O that we breathe, versatile carbon, C that forms the backbone of life, and strong iron, Fe, used in construction. You can find a complete list of all known elements neatly organized on the periodic table, a chemist's best friend. Compounds, on the other hand, are pure substances formed when atoms of two or more different elements combine chemically in a fixed whole number ratio. Common examples include water, H2O, formed from hydrogen and oxygen in a 2-to-1 atomic ratio, and table salt, NaCl, formed from sodium and chlorine in a 1-to-1 atomic ratio. It's vital to note that the properties of a compound are typically very different from the properties of the individual elements that constitute it. For instance, sodium is a reactive metal, and chlorine is a toxic gas, but together they form harmless table salt. Now let's shift our focus to mixtures. A mixture is a physical combination of two or more pure substances, elements or compounds, that are simply mixed together but are not chemically bonded to each other. A key characteristic of a mixture is that each individual substance within the mixture retains its own original chemical identity and properties. A great everyday example is a fresh garden salad. You can still easily identify and distinguish the lettuce, tomatoes, cucumbers, and any other ingredients. Their individual characteristics are preserved. Another common example is salt water. It's a physical mix of salt, a compound, and water, another compound. You can often separate the components of a mixture using various physical methods, such as filtration, to separate an undissolved solid from a liquid, distillation, to separate liquids with different boiling points based on volatility, or evaporation, to separate a dissolved solid from a liquid by turning the liquid into gas. Mixtures themselves can be classified as either homogeneous or heterogeneous, based on the uniformity of their composition throughout the sample. A homogeneous mixture has a completely uniform composition throughout its entirety, meaning it has only one phase. This means that you cannot visually distinguish the different components. It looks the same from top to bottom, and any sample taken from the mixture will have the same composition. Salt water, once the salt is fully dissolved, is a perfect example of a homogeneous mixture, as is clean air, a mixture of nitrogen, oxygen, argon, and other gases. Conversely, a heterogeneous mixture does not have a uniform composition. You can easily see and identify the different components or distinct phases within it. Think of a mixture of sand and water, where the sand settles at the bottom, or a chocolate chip cookie, where the chocolate chips are clearly distinct from the dough. Understanding this crucial classification is extremely important for NEET, especially when you start dealing with concepts like solutions, homogeneous mixtures, colloids, suspensions, types of heterogeneous mixtures, and various separation techniques used in the laboratory. Section 5. The Rulebook of Reactions, Laws of Chemical Combination, Part 1. When substances react to form new substances, they don't just do it randomly or haphazardly. Oh no, there are rules. These rules are called the laws of chemical combination. They are fundamental principles discovered through meticulous experimentation that govern how elements combine to form compounds and how substances interact during chemical reactions. Understanding these laws is like having the secret code to deciphering chemical reactions and predicting their outcomes. They were painstakingly discovered by brilliant scientists through careful observation and quantitative measurements, laying the groundwork for modern chemistry. Let's explore some of these foundational laws that every NEET aspirant should know by heart. These laws are your friends. First up is the law of conservation of mass, a truly monumental concept proposed by the brilliant French chemist Antoine Lavoisier in the late 18th century. This law states that in any chemical reaction, matter is neither created nor destroyed, it simply changes form. In other words, the total mass of the reactants, the starting stuff you mix together, is always equal to the total mass of the products, the new stuff that is formed after the reaction. Imagine burning a wooden log in a fireplace. It seems to disappear and turn into ash, but if you could somehow collect all the smoke, gases like carbon dioxide and water vapor, and the ash, their combined total mass would be exactly equal to the original mass of the log plus the mass of the oxygen from the air that it reacted with. Mass just gets rearranged. Next, we have the law of definite proportions, also known as the law of constant composition. This important law was formulated by the French chemist Joseph Proust around the turn of the 19th century. This law states that a given chemical compound, regardless of its source or method of preparation, always contains its component elements in a fixed ratio by mass. For example, pure water, H2O, always consists of approximately 11.19% hydrogen and 88.81% oxygen by mass. Whether the water sample comes from a river, a tap, a raindrop, or is synthesized in a laboratory, that specific mass ratio of hydrogen to oxygen will always remain the same. This consistency is what defines a specific chemical compound. Think of it like a very precise recipe for baking a cake. To make a specific type of cake, you always need a certain amount of flour, sugar, eggs and butter in a fixed, predetermined ratio. If you significantly change the ratio of these ingredients, you'll end up with a different kind of cake, or perhaps something that isn't a cake at all. Similarly, elements combine in specific unvarying mass ratios to form specific chemical compounds. This law was incredibly crucial in establishing that compounds have a definite, unchanging chemical formula and composition. It's a cornerstone of quantitative chemistry and helped chemists understand that substances combine in predictable ways, paving the way for Dalton's atomic theory. It tells us that compounds are not just random jumbles of elements. Section 6. More chemical laws. The foundation of how things combine, Part 2. Let's continue our exciting journey through the amazing laws of chemical combination. These laws are not just historical footnotes. They are active principles that help us predict and understand how chemical reactions happen every single day, all around us and even inside us. They are like the fundamental grammar rules for the universal language of chemistry. Knowing them thoroughly will make more advanced concepts like stoichiometry, chemical equilibrium, and thermodynamics much easier to grasp, which is super important for your NEET preparation. So let's dive into a few more of these foundational principles that underpin all chemical interactions. Get ready for more science. John Dalton, whose atomic theory we'll discuss soon, also came up with the law of multiple proportions. This clever law states that if two elements can combine to form more than one distinct chemical compound, then the masses of one element that combine with a fixed mass of the other element are in ratios of small whole numbers. Consider the elements carbon and oxygen. They can combine to form at least two common compounds: carbon monoxide, a toxic gas, and carbon dioxide, a greenhouse gas essential for plant life. If you take a fixed mass of carbon, say 12 grams, you'll find that it combines with 16 grams of oxygen to form carbon monoxide, or with 32 grams of oxygen to form carbon dioxide. The ratio of the masses of oxygen that combine with the fixed mass of carbon is 16 to 32, which simplifies to a simple whole number ratio of 1 to 2. Simple, yet incredibly profound, and it strongly supported the idea of atoms. Then there's Gay-Lussac's law of gaseous volumes, another gem from the early 19th century, discovered by the French chemist and physicist Joseph-Louis Gay-Lussac. This law specifically deals with reacting gases. It states that when gases react together to form other gases, and when all volumes are measured at the same temperature and pressure, the ratio of the volumes of the reacting gases and the gaseous products can be expressed in simple whole numbers. For example, experiments show that 2 volumes of hydrogen gas react with 1 volume of oxygen gas to form 2 volumes of water vapor. The ratio of the volumes is 2 to 1 to 2. This observation was crucial and hinted at the relationship between gas volumes and the number of particles involved. Finally, let's talk about Avogadro's law, proposed by the Italian scientist Amedeo Avogadro in 1811. This law is a cornerstone of chemistry and states that equal volumes of all gases, when measured at the same temperature and pressure, contain an equal number of molecules or atoms if the gas is monatomic like helium. This was a truly groundbreaking idea at the time. It means that if you have a 1-liter container of oxygen gas and a 1-liter container of nitrogen gas, both at room temperature and atmospheric pressure, they both contain the exact same number of molecules. This law provided a vital link between the macroscopic world, measurable volumes of gases, and the microscopic world, the actual number of molecules, and it was instrumental in determining atomic and molecular masses. It also helped clarify the difference between atoms and molecules. Section 7. Dalton's big idea: atoms are awesome. Now let's talk about atoms. The idea that matter is composed of tiny, fundamental particles isn't entirely new. Ancient Greek philosophers like Democritus pondered this very concept thousands of years ago, calling them atomos, meaning indivisible. However, it was John Dalton, an English chemist, physicist and meteorologist, who, in the early 1800s, brought the concept of atoms into the realm of quantitative science with his remarkably insightful atomic theory. His theory wasn't just philosophical speculation, it was based on the experimental laws of chemical combination we just discussed. It revolutionized how we think about matter and its behavior. It's truly the foundation of modern chemistry. Atoms, as Dalton envisioned them, are the basic, ultimate building blocks of everything in the universe. Dalton's atomic theory, first presented in 1808, had several key postulates that provided a framework for understanding chemistry. First, he proposed that all matter is made up of extremely tiny, indivisible particles called atoms. Think of them as super tiny fundamental Lego bricks that cannot be broken down further by chemical means. Second, he stated that atoms of a given element are identical in all respects, including mass and chemical properties. So all gold atoms are exactly the same as every other gold atom, but they are distinctly different from, say, silver atoms. Third, Dalton postulated that atoms of different elements differ in mass and possess different chemical properties. This inherent difference is what makes each element unique and gives rise to the diversity of matter we observe. His fourth postulate was incredibly important. Atoms can neither be created nor destroyed during a chemical reaction. They are merely rearranged, combined, or separated. This elegantly explains the law of conservation of mass. If atoms are just shuffled around, the total mass must remain constant. And fifth, Dalton proposed that atoms of different elements combine in simple whole number ratios to form chemical compounds. For example, in water, H2O, hydrogen and oxygen atoms combine in a 2-to-1 ratio. This postulate directly explains the law of definite proportions and the law of multiple proportions. See how beautifully it all connects and makes sense? Dalton's theory provided a powerful, logical and particle-based framework for understanding chemical behavior and reactions. While some specific parts of Dalton's original theory have been modified in light of later discoveries, we now know that atoms can indeed be divided into subatomic particles like protons, neutrons and electrons, and that isotopes of an element exist, meaning atoms of the same element can have slightly different masses, its core ideas remain fundamentally valid and incredibly important. It was a giant leap forward for science. It gave us a tangible, particle-based view of matter and reactions, moving chemistry from qualitative observation to quantitative prediction. For your NEET studies, understanding Dalton's contribution is absolutely crucial, as it sets the stage for understanding atomic structure, chemical bonding, periodicity, and the all-important mole concept. Atoms are indeed awesome, and Dalton helped us see that. Section 8. Counting atoms, the mole concept and atomic mass. Atoms and molecules are incredibly, unimaginably tiny. We can't see them individually, even with the most powerful optical microscopes, and we certainly can't pick them up and count them one by one for a laboratory experiment or a chemical reaction. So, how do chemists manage to work with such minuscule particles in a practical, quantitative way? They use a special unit called the mole. No, I'm not talking about the furry little creature that digs tunnels in your garden, though that's a fun thought. In chemistry, a mole, abbreviated as mole, is a specific unit for counting a truly enormous number of particles, such as atoms, molecules, ions, or electrons. It's like a chemist's version of a dozen, but on a vastly, vastly larger scale. 1 mole of any substance contains Avogadro's number of elementary entities, particles. Avogadro's number, symbolized as Na, is a very large constant experimentally determined to be approximately 6.022 times 10 to the 23rd particles per mole. That's 602 sextillion, 200 quintillion particles. It's a massive number because atoms and molecules are so incredibly small. So, if you have 1 mole of carbon atoms, you have 6.022 times 10 to the 23rd carbon atoms. If you have 1 mole of water molecules, H2O, you have 6.022 times 10 to the 23rd water molecules. This brilliant concept allows chemists to connect the macroscopic mass of a substance, something we can weigh in the lab, to the actual number of microscopic particles present in that sample. It's a bridge between two worlds. To effectively use the mole concept, we also need to understand atomic mass and molar mass. The atomic mass of an element is the average mass of its atoms, typically expressed in atomic mass units, AMU. You can find these values listed for each element on the periodic table. For example, the atomic mass of carbon, C, is approximately 12.011 AMU, and for oxygen, O, it's about 15.999 AMU. The molar mass, M, of a substance is defined as the mass of 1 mole of that substance, and it is conveniently expressed in grams per mole, G-mol. Numerically, the molar mass of an element in grams per mole is equal to its atomic mass in AMU. So 1 mole of carbon atoms with an atomic mass of approximately 12 AMU weighs approximately 12 grams. For a compound, the molar mass is the sum of the molar masses of all the atoms in its chemical formula. The mole concept is super duper important for your NEET exam and for all of chemistry. It acts as the central bridge connecting the microscopic world of individual atoms and molecules with the macroscopic world of grams, kilograms, liters and milliliters that we can actually measure and work with in the laboratory. It allows us to perform quantitative chemical analysis, calculate how much of a particular reactant we need for a specific chemical reaction, or predict how much product we can expect to obtain. Mastering mole calculations, converting between mass, moles, and number of particles is absolutely essential for solving problems in stoichiometry, solutions, gas laws, and many other areas of chemistry. So don't be afraid of it. Embrace the mole. It's your indispensable friend in the world of chemistry. Section 9. Recipe for reactions, stoichiometry, and balancing acts. Now that we've learned how to count atoms and molecules using the magnificent mole concept, let's talk about the quantitative aspects of chemical reactions. Stoichiometry, stoichiometry, is the branch of chemistry that deals with the quantitative relationships between reactants, the starting materials, and products, the substances formed, in a chemical reaction. That might sound like a very complicated and intimidating word, but at its heart, stoichiometry is really like following a very precise recipe. A good recipe for a cake tells you exactly how much of each ingredient, flour, sugar, eggs, you need to make a certain amount of cake. Stoichiometry does the exact same thing for chemical reactions, telling us the amounts of substances involved. The very first and most crucial step in any stoichiometry problem is to have a correctly written and balanced chemical equation. A balanced chemical equation accurately represents a chemical reaction by showing the chemical formulas of the reactants on the left side of an arrow and the chemical formulas of the products on the right side. More importantly, a balanced equation has the exact same number of atoms of each element on both the reactant side and the product side. This is a direct consequence of the law of conservation of mass. Atoms are not created or destroyed in a chemical reaction. They are simply rearranged to form new substances. Balancing chemical equations usually involves adjusting the stoichiometric coefficients, the whole numbers placed in front of the chemical formulas, until the number of atoms of each element is equal on both sides. Once you have a properly balanced chemical equation, the stoichiometric coefficients in that equation provide you with the mole ratios of the reactants and products involved in the reaction. For example, consider the balanced equation for the formation of water from hydrogen and oxygen. 2H2G plus O2G yields 2H2OL. The coefficients tell us that 2 moles of hydrogen gas, H2, react with 1 mole of oxygen gas, O2, to produce 2 moles of liquid water, H2O. These mole ratios, for example 2 mole H2 per 1 mole O2 or 1 mole O2 per 2 mole H2O, are incredibly powerful conversion factors. If you know the amount, in moles or mass, of one substance involved in the reaction, you can use these mole ratios to calculate the exact amount of any other reactant needed or any product formed. Sometimes in a chemical reaction you might not have the reactants mixed in the exact stoichiometric proportions indicated by the balanced equation. You might have more of one reactant than is needed to completely react with another. The reactant that gets completely consumed or used up first in a chemical reaction is called the limiting reactant or limiting reagent, because it limits the maximum amount of product that can be formed. The other reactants, which are present in a greater amount than necessary and are therefore not completely consumed, are called the excess reactants. Identifying the limiting reactant is a common and very important type of stoichiometry problem you'll frequently encounter in NEET and in practical chemistry. It's like making sandwiches. If you have 10 slices of bread but only 3 slices of cheese, and each sandwich needs 2 slices of bread and 1 slice of cheese, the cheese is the limiting reactant, and you can only make 3 sandwiches even though you have bread left over. Section 10. Conclusion. Your chemistry adventure awaits. Wow, we've certainly covered a lot of essential ground together on this chemical journey. From exploring the very nature of matter and its different fascinating states, solid, liquid, gas, oh my, to understanding the fundamental laws that meticulously govern how substances combine and react with one another. We've also peeked into John Dalton's revolutionary world of atoms, learned the indispensable skill of how to count these incredibly tiny particles using the amazing mole concept, and even figured out how to use chemical recipes with the principles of stoichiometry and balancing equations. These concepts are truly the fundamental building blocks of chemistry, and developing a strong, intuitive understanding of them is absolutely key for your success in the NEET examination and beyond, in any science-related field you pursue. Remember folks, chemistry is not just about passively memorizing isolated facts, disconnected formulas, and long lists of reactions. It's much more profound and exciting than that. It's about actively understanding the underlying principles, seeing the connections between different concepts, and then applying that knowledge to solve real-world problems and predict how matter will behave. Think of it like assembling a giant, intricate puzzle. Each concept we've discussed, matter, states, laws, atoms, moles, stoichiometry, is a crucial piece, and when you put them all together correctly, you begin to see the bigger, beautiful picture of how the world works at a molecular and atomic level. The examples we discussed, like water-changing states or a recipe for a chemical reaction, are happening all around you all the time. The journey to mastering chemistry, especially for a competitive exam like NEET, undeniably requires consistent effort and dedicated practice. Lots and lots of it. Work through as many different types of problems as you can, from simple conceptual questions to complex multi-step calculations. Review the core concepts regularly to keep them fresh in your mind, and most importantly, don't ever be afraid to ask questions when you're unsure about something. Use visual aids like diagrams and flowcharts, create your own summary notes, and always try to connect what you're learning in the textbook to tangible, real-life examples. The more actively you engage with the material, the more comfortable, proficient, and confident you'll become. Think like a scientist. Observe carefully, question everything, and experiment, even if they are just thought experiments in your mind. So keep exploring this incredible field. Chemistry is a vast, dynamic, and endlessly fascinating subject. What we've covered in this guide are the foundational basics, but they are the solid bedrock upon which all other, more advanced chemical knowledge is built. Embrace the challenge with enthusiasm, stay curious and inquisitive, and always remember that every single bit of effort you put in now will undoubtedly pay off in the long run, helping you achieve your academic and career goals. You've got this. Now go forth, armed with this knowledge, and conquer the world of chemistry, one atom, one mole, and one reaction at a time. Science rules, and so do you for learning it.